they're like research projects. Like it's kind of like a problem where it's like there's no like one answer. You just have to figure it out.
Okay.
You know, and he's like give you like feel like they write out.
Whatever.
Graph and stuff. The first one was actually interesting. That's pretty cool. The second one looks cool, but I haven't really started it.
You know, Prognos is so fun. What are you gonna do? Prognos is like a review of right out this with slightly more.
Oh,
That's the professor you had.
Yeah, I think it's the project.
I think if you had 11 undergrad, it'd be exactly the same.
I don't know, maybe I'll.
did you have that was like
Yeah, Gabo was so. He was like,
yeah,
I was like, you know, I've never met a professor that's so like,
He's so like willing.
yeah, it's just we're hoping the board out. Well, this is a lot of predictions.
It was like kind of thin.
Okay, I should make it wider.
Yeah, they are.
Okay. Alright, fine.
I'm not like, you should actually just don't split up at all, just right vertical.
Alright, fine. We'll do it the way he split it. It's basically board by board, right? Okay. Is that good enough? Yeah. I don't know what I'm doing, man. Wait, what time is
You do
it?
the dotted line.
I don't know how to do. Does anybody know how to do that?
Let's figure it out right now.
Yeah, you have to impress the student.
Yeah. Or is it this way? No. I'm just embarrassing myself. Wait, does anybody know the material that I'm covering or no?
Yeah. What are you covering?
Commutator subgroups and their properties. Okay.
There was one with the
Scalar field. That was one of the scalar.
Okay. Is it okay if I just write some of the theorems out that I have to prove so I don't have to write it later?
Wait, what is this?
All right, mister. All right, we get it.
You're live streaming it? We have a chat? Is anybody in chat? Oh my god, there's a Twitch chat, bro.
Actually, I'm not gonna spoil it.
Oh, man.
You can Venmo it.
Oh.
Oh.
That's bad
Can
luck,
I
right?
get an F in the chat?
It's like 10 years of bad luck. Let me know when. How's everybody doing? Hi. Everybody doing good? Good? I'm gonna do the Damiano thing now. Huh?
What?
He's doing great.
I'm just a happy guy.
Pretty good. I'm just happy guy.
Oh, there's actually people. Wait, who's here? All right, whatever. No, I'm just, people want to watch. And yeah, I'm just recording it / streaming, so. Is that cool with everybody?
When I go up to present, please don't.
Yeah.
Okay.
You got it. I'm gonna turn it off right when I finish. All right. Good. All right. Okay, so my topic's about commutator subgroups. I'm gonna start with some exposition, and it kind of relates to some questions I asked Professor Damiano last time after we learned about slope subgroups and all that theory. He gave me some information, and I want to share that with you, and it's an analogy. Essentially, if you want to learn about somebody, and say you can't ask questions to that person directly to get to know them, right? What can you do? You can possibly go to the friends or people that know them and ask them questions about what do they like to eat, who are they as a person, what's their personality, what hobbies do they have, do they like to bowl, how good are they at bowling? Anyways, bowling mention, that was there, yeah. Okay, so the basic idea is that this analogy is kind of related to group actions and groups, where you have groups acting on sets through this group action. And you learn about these groups by studying the group actions that exist from this group G to a set. And we learned that through the producing certain group actions that are associated with certain sets, we learned about how every arbitrary group has structure that when you look at the prime factorization of the order of a group, there's all these nice solid P subgroups. How that relates to the lecture today is that instead of studying a group directly, we're going to look at the quotient group of a group. So let G be a group, and we're going to study instead the quotient group G over N, where N is a normal subgroup. Okay. Now, some other things that are in the background is that there's a lot of nice abelian group theory. I don't know any of it, but it exists. But the basic idea is, wow, I'm so bad at this. Okay. You're a mathematician, and you have all this nice theory. You can obviously apply it to abelian groups, but what happens when you have a non-abelian group? What do you do? There's this notion in computer science called reductions. Essentially, you want to transform the non-abelian group into an abelian group so you can use this theory. How do we do that? Well, we know that there's a canonical homomorphism between G and the quotient group. And what we do is we abelianize G by looking at the quotient group and finding out exactly when is this abelian, right? So the idea is we want to find a precise way to find when this is abelian. This is if and only if, right? The cosets commute. So for all xy within G, you have that x n, y n, these two cosets, they commute. So y n times x n. And using the law of composition for quotient groups, you have this. Doing some algebraic manipulations, you just take the inverse of these, multiply on both sides. You have x, y, n is equal to n. And using the theory of cosets, we know that this weird-looking element is in n. Okay. So we've proved something here, and what this is saying is that when we want G over n to be abelian, we want all these elements of this form to be in this normal subgroup of G. Now we're going to formalize these notions. This is going to be what we call a commutator. And so, bless you. Each of these commutators is going to be in this normal group. So if you take the finite product of all these commutators, that's obviously going to be in there. We find basically the set of all finite products of these commutators forms a subgroup called the commutator subgroup. So those are our first few definitions. And this is kind of like a very natural way a mathematician might go about this. You don't start from the definition, you start from seeing this and then defining things. All right, so the commutator of y in G is defined in this way. y, x, y, exactly what we see here. And this is the second definition, which is the commutator subgroup. So let G be a group. We define with this notation just means commutator subgroup. This is equal to the subgroup generated by the commutators of G, x, y, and G. Okay. Other standard notation is that this is G prime. From what I read, this is a derived subgroup, and that's why we use this little apostrophe here, because derivatives, derived. All right. One thing to note here is that this is obviously a subgroup. You've taken elements from G and generated a subgroup, so this is going to be a subgroup of G, this group right here. Let's see. Okay, yeah, so we're now going to formalize this theorem using these notions into theorem 3.10. I'm going to write it over here. n be a normal subgroup in G. Yeah, G over n is abelian. If only if G prime is a subset of n. That's basically what we're saying here. Bidirectional, we're going to do one direction first. One direction. So assume G over n is abelian. That means that for all x, y, and G, we have what we had over there. So xn, yn, to yn, xn, doing some same things that we did. This is true. Okay. Saying that all the commutators are in n. So now we're going to now prove this part. So this is kind of the build up to this. Let x be in G prime. I need to show that x is, sorry, let's call this A. This is in n. A is in this commutator subgroup, meaning that A is a finite product of commutators. I'm going to call each of these commutators x1 to xk. K being an integer greater than or equal to 0. Okay. Since we've proved here, or it's true that each of the commutators is in n, so each individual commutator in this finite product will be in n. You write it out. That means that this whole finite product will also be in n by closure of subgroups. And that finishes that direction. Yes.
So you suppose that G over n was abelian, and that's why you got like commutators in n.
Right. Yeah. So assuming this, you get this.
Yeah.
Apply it here. It goes through.
So where are like the x1 to xk?
Yes. So these are the commutators. Basically, when we're proving this, we're saying that A is an element in here, right?
Yeah.
G prime is a set of all commutators in G. They have this form.
Yeah.
I'm just saying that each of these individual things are this form.
Or in that form.
Yeah. Does that help?
Yeah.
A little bit? What's like?
I guess I don't know. Like the commutator is like that form. I thought like x inverse y inverse.
Right. Yeah, but we don't necessarily need to expand it out. We just like instead of using, we don't necessarily need to use this expanded form.
Yeah.
Because all we need to prove is that each individual commutator is in n.
Okay.
Once we show that, this whole product will be in
And that means that like Gn is a subgroup.
exactly right subset. Yeah.
Why are you taking a product again?
Oh yeah. So it's because this is a how do I say it? It's a subgroup generated by the commutator. So you can have like the definition of this is you take any finite product of commutators or the inverse of a commutator to find all the elements in this subgroup that's generated in here. Does that make sense? Like this, or
Oh, it's a sick.
like this is
It's like a group generated by the commutator.
It's a group
right.
generated.
So this is like equivalent to saying that xi. No, sorry.
Oh, okay, I see. So you're
Yeah.
generating a group based. on-
Using these elements, these all name like a specific element. They're just
So why don't those have like exponents then?
oh well, like this is one individual. You could put it to some exponent here. Sorry, I could like it's either 1 or -1 here. And then like whatever elements are equivalent, that's how you get like powers of 3, for example. So if you have like x1 and x2 being equal to the same commutator, then their powers kind of.
So in here, the issue that so the xi, they're not elements in G, but they are think of these as commutators. So
Yeah.
xi should be
Yeah.
like commutator xi yi.
Okay.
Right, yeah. Each xi is equal to like let's see. AI, VI, XI. Where AI, VI are all elements in G. So you could rewrite it in that way. It's just like this is just for compactness.
Yeah, that makes sense.
All right, so we're gonna go the other direction. So we're gonna assume this. Okay, So we know that G over N is abelian if and only if this is true. So we just need to prove that each commutator is an N. Let A be a G. That means A has a form for X, Y, and G. Okay. We know that A is going to be in G prime. Yeah. And since we assume this, that means that A is also going to be in that. Wait, yeah. That's true, which means this is equal to that, right? So we proved this. This is true, that's true. We proved this out because we're proving here that quotient group is a period. Make sense? All right.
Like in other words, just taking two cosets, say xn and yn, you want to show that they commute. As proved in the first blackboard.
Right.
This is equivalent to showing that the commutator between x and y is in n, and is what?
Yeah. Yeah. So just take that, move it over here, and yeah. Okay. Okay. I'm gonna get rid of this now. Okay. So just a little remark. Just to understand commutators a little better. I probably should have done this a little earlier, but whoops. Is equal to 1. So a commutator in G is equal to 1, if and only if X and Y commute. Is this obvious to everybody, or do I need to prove it? No. Okay. Okay. So that's done. There are two corollaries of theorem 3.10, if I wrote it, yeah. Before we get into that, there's a sublemma here, or a lemma that we're going to be using. It's that this commutator subgroup is actually a normal subgroup of G every single time. So let G be a group. And we have G prime is a normal subgroup of G. Okay. So this is equivalent to proving that for all G and G, or for all G and G prime, or A and G prime, and for all G and G, then the conjugate GA G prime, or GA G inverse is in G prime. So let A be G prime and G and G, proving that. So since this is in G prime, using the same notation from before, hopefully it makes more sense now. It's going to be a finite product of commutators. And if we look at G, A, G inverse, this is going to be equal to either conjugating the whole product or conjugating each individual commutator. And the G and G inverses on the inside, they'll cancel out with each other. So we have yeah, everybody see why these two are equivalent, right? Okay. Now, all we need to do is to show that if this is an M, or to show that this is in, sorry, not M, in G prime, you just need to show that each individual conjugation of each commutator is in G prime. So, little lemma will prove that for all G and G, say Z, a commutator, G, Z, G, 1 is a commutator. Okay, I'm going to prove that. Okay. So since A is a commutator, it has the form Z, sorry. Yeah. Thank you. X, Y, N, G. Okay. So if we look at this, again, we're going to do the same thing that we did over here. Expanding Z out, it's X inverse, Y inverse, XY. So we'll do the conjugation for each individual one. You'll notice that this is the inverse of that, and this is the inverse of that. So if we set this to S, and this to T, then this is all equivalent to the commutator of S and T. Does everybody see that, or should I write out a little bit more? Okay. Yes, no?
Oh, so,
Yeah.
S, T.
Yeah.
So it's like T inverse, S inverse, T inverse, S, T.
Right, where
Oh,
S is
okay.
defined as that, T is defined as that. This is S inverse, it's equal to T inverse. Okay. Yeah, so we show that when you conjugate a commutator, it's a commutator. Each individual of these is going to be in G prime. Take a finite product, this overall thing is in G prime. So that means that G prime is null in G. Okay. Nobody needs these definitions, yeah? All right, so following. God, it's so fucking short. Okay. Fine. So from G via homomorphism. Okay. Where A is abelian. Wow, that's great. Then G prime is a subset or inside the kernel. Okay. So we have a homomorphism. Yeah, all right, we're gonna just use the first isomorphism theorem. And by that, we know that G over the kernel of phi is isomorphic to the image of phi. That's a subgroup of A. We proved this before. Now, since A is abelian, that means that any subgroup of an abelian group is abelian. Isomorphism, this is abelian. Yeah? Yeah.
So.
Okay, so.
Yep.
Yep. Yeah. Okay. So. Okay. Now, using theorem 3.10, we let n to be the kernel of phi. Over here. It's abelian if and only if G prime is in the kernel. So that finishes the proof. Good? Yes. Yeah. 2 minutes. Okay. Last corollary. H, nope. G prime, again, the commutator subgroup. Okay. I think I'll just give the proof sketch for this, just give the idea, and then I think the details will come to light from that. So G is a group, H is a group, G prime is the commutator subgroup. So we really have this relationship between the groups, or the sets. Notice that H contains G prime. So the idea is here is to use the correspondence theorem, where if we can produce a homomorphism from G to G prime, then what we can do is, if we look at the subgroup, through the correspondence theorem, since this is a subgroup of this, there's a corresponding subgroup of G by way of the inverse image of G, that. And this is going to be equal to H, because we're looking at all the elements that map to the cosets of G prime in H. What is that? You take elements in H. Okay. So we have the canonical homomorphism. Sorry, this is like kind of messy. So we start with the canonical homomorphism. This. We know that H over G prime and G over G prime, they're subgroups, or this is a subgroup of that. We know that this is abelian because of theorem 3.10, which I erased. Essentially, if you take n to be G prime, then since G prime is normal in G, then you have this as abelian.
That's correct.
Yeah. Okay. So this is going to be abelian. It's also going to be normal, which means that through the correspondence theorem, the corresponding subgroup, this H, is going to be normal in G. And that kind of finishes the proof without writing all the details. That's the general idea. And that's it.
All right.
Question?